Thank you for tuning into the Group Theory Podcast. This is the show where we interview working mathematicians about what it's like to do research for a living. My name is Logan, and I'm sitting here with Michael, across from Dr. Ruxandra Moraru, Professor Extraordinaire here at the University of Waterloo in the Faculty of Mathematics. Dr. Moraru, as well as being professor here at Waterloo, has done extensive work with the Perimeter Institute for Theoretical Physics, and needless to say, through her many publications, has made an impact on the mathematics and theoretical physics communities, and as her students as well. So, how are you doing today, Doctor?
I'm very well, thank you.
Perfect. So, I guess we'll just jump in then. So, the first question we have for you is kind of like, what's your field of research, and kind of how would you describe it to like a non-mathematician?
So, I think that geometry is always so I'm a geometer, and then but the objects that I study do come from physics. So, I wouldn't say that I'm necessarily a mathematical physicist in the sense that I only work on objects that come from physics, but I am interested in structures and objects that come from physics, and I try to describe their properties, their geometric properties, and I think that geometry is maybe somewhat difficult to describe because I would just say that maybe geometry is the study of structures or maybe of objects or sets trying to understand some of their properties, but I know it is very vague because you may say something like their geometric properties. So maybe I'll just give you a very simple example. So suppose that it's very natural to maybe have a problem, and then when you're describing the problem, come up with a set of equations that are associated to the problem. So if these equations are polynomial, you're just solving a system of polynomials. And that can be very difficult, even if you have just one polynomial, finding and when I say that polynomial equations, maybe you're finding the zeros of a common set of polynomials. So even if you have just one polynomial, it can be very difficult to find all the roots of the polynomials, which are the zeros. And so even though the fundamental theorem of algebra tells you that if you have a degree n polynomial, you have n roots, you may not be able to find all the n roots. So if you're a geometer, so here if you're studying polynomial equations, you're more of an algebraic geometer, you may tell yourself, okay, I have no hope of finding all the roots, but I'm going to study the properties of this set. So I know that this set of solutions is now a set that has n points. And maybe my polynomial has certain properties, so I know I can spot that there are some repeated roots, or etc. Or obviously, very quickly, you will want more than one polynomial. Oh, this was if you had a polynomial of one variable here. But anyway, but the point is that you will start studying, instead of hoping to find all the solutions, you will instead focusing on the set of all solutions and what properties does it have. Okay, and this is where the geometry comes into play. Right? And then maybe if you're now thinking of the set as imagining the set of solutions as points inside, let's say you're over the reals, maybe in Rn, because you have n variables, polynomials of n variables, then your sets of points will now describe subsets of Rn, and you may want to think to describe their geometric properties. So here, if you're very much an algebraic geometer, you'll just use algebra. So you'll try to describe all these properties using properties of the ring of polynomials and the ideals, etc. If you're more of a differential geometer, you'll start using analysis and calculus. And if we're going to, let's say we pick something very simple, like a zero set of a polynomial of two variables, which now will give you a subset of R2. Then using maybe some calculus, you may want to try to determine the different shapes. So now your subset will be just a curve in R2, but you want to maybe distinguish between the curves in R2, because if you just draw simple examples, you'll feel, for example, if your subset is a line, it will feel very different from a parabola, and you're trying to define a quantity that will really enable you to distinguish between the two. So one notion you could use is the notion of curvature. So the line is not curved at all, whereas the parabola, it does curve, and not only that, but it feels as you're going through the curve that it curves at different rates. So you will want to, you will define something like curvature to try to distinguish between the two, these two sets. And so I guess this is where the geometry comes into play, right? That you're trying to find ways of describing sets of objects that intuitively feel different, but you're trying to find some extra quantities, invariants, etc., that will help you distinguish between these objects. Okay.
Right. Okay.
So, whereas maybe an analyst would be just interested in more like the analytic properties of, well, often maybe functions or but in geometry yeah, exactly. You're often you're looking at a set and maybe some kind of structure on it. And often the reason you put a structure is because you're trying to distinguish between objects and trying to find certain properties of the sets that will enable you to distinguish them.
Okay. That's quite the definition.
Okay.
Yes. No, very
It's
good.
not a definition, it's just, I don't know. I always find it's complicated. Number theorists will have a shorter answer.
Yeah.
But in geometry, I don't know. What is geometry? I would say the study of structures, I guess.
Yeah.
Okay.
I think it's a good answer, yeah. I was actually going to ask, do you find that there's a lot of physical weight, weight for the physical side of the term geometry in higher level mathematics? So what I mean by that is, do you find that a lot of the higher level mathematics and geometry is motivated by physical concepts still, or does it become a more abstract term?
Well, I think that a lot of concepts can become very abstract, but if you look at the root of the concept, often it's motivated by something that was quite physical.
Right. Okay.
So, yes, exactly. So even though you may no longer be able to attach it to something that's very physical in its more abstract form, the concept at its root, and when you start with more simple cases and examples, are usually coming from something that's physical. And I guess when we're saying physical, it can even be just a picture, right? I mean, so I guess I would say yes.
Okay.
Absolutely. Okay.
Go ahead.
Well, one thing that I think is pretty interesting, so you're in the Department of Pure Math here, right? But, I mean, it says even on your profile that you're interested in, the applications to physics. So I'm just wondering, where do you kind of draw the line between something that's, say, pure math and something that's more applied math or more theoretical physics? Like, how do you differentiate those two things?
I mean, the applications of my work are really in very theoretical physics, but maybe the difference would be that for what I work on, I'm not completely motivated by the physics, whereas someone who would be more I don't know, it's not good to label things, but if you will have people who do mathematical physics who are purely motivated and only studying objects that come from physics and only looking at the properties that serve the physics. Maybe that's one way of putting it. Whereas for me, okay, I do focus more on objects that come from physics, but then I just treat them as an interesting math object. And then, I find that some parts of it will be interested in mathematically, but, maybe the physicists are not so interested in those parts of the problem or those properties. But for me, it's not so much of a concern. You study what's interesting or what you find is interesting, but... And now I have a student, because I'm cross-appointed with the physics department, because now I have a student who is doing a PhD with me, but he is a physics student. And the problem we're working with, we have a physicist at Perimeter that's also is a co-supervisor. And the problem he is studying is really coming from physics. But we're just looking, so you have these structures that help model this some physical properties, and we're only trying to just understand the mathematics of the structures, and they're quite new, so there's a lot of just groundwork to, basic properties that need to be figured out, and more basic results that need to be worked out that are quite natural. But or at least I'm just focusing on the math, on what I can understand. I mean, I've been around in physicists enough and gone to physics talk enough to maybe place a little bit how they're using some of my objects, but I don't pretend to understand any physics because I haven't done physics since high school myself. But not that I don't want to, there's just not enough time. Then when I started math, I was quite happy just with the theory, and I was not interested so much in applications. Well, it's not that I was not interested. I was very happy just playing with the math itself, and it's just little by little, and I quite like I mean, it's interesting to see how things are being used.
Yeah,
I think that's particularly interesting though in your case here, because there's so many mathematicians who like do their work in like an abstract field like category theory, and they'll never in their entire lifetime see it be used in any kind of real physical process, right? So I guess the work you do, say, with the University of Waterloo, how does that compare necessarily to the work you do with Perimeter, right? Are they different at all, or is it just kind of...
No, it's the same.
Same kind of thing?
I think it's just because I have certain expertise. Even now, I was in California a couple of weeks ago at this workshop where it was really much a workshop where it's at the American Institute of Mathematics, where the premise is that they get maybe 20, 25 people together, and you kind of discuss, there's a theme for the workshop, and they get people with expertise that are tied to the theme, and then you kind of discuss what are potential open problems, and you work on it. And half of the people were there were physicists, and not everyone worked on the same problems. There were all these open questions, and you chose which problem to work on. And I happened to be part of a group of 4 people for the week where there were 2 physicists and 2 mathematicians, and the physicists were trying to understand some things, and both of us, the mathematicians, had the expertise, and we were able to properly formulate mathematically what they wanted, and then start really working and describing in detail what they were interested in, right? So I think that's the same thing with Perimeter. My interaction with the physicists there, it's more, okay, I have certain expertise, and they're interested, go, oh, about this. What I have here kind of either uses these objects or is similar to these types of structures. Like, what can you, what can you say about what I'm trying to do here? And it depends on the physicist. Sometimes some of them do have an extensive math background, so there is a common language, and so the discussion is very smooth. And others, it takes a lot of back and forth, to kind of understand a little bit what they're trying to tell me, and then them understanding what I'm telling them. But it's okay. But just to answer your question, it's not like I'm doing very different work. I'm just applying my knowledge to the particular questions that they're interested in.
Okay, that sounds awesome. I mean, it's great to work in like a huge community like that. You all get to work on a whole bunch of different problems. Now we do have to ask though, because you are affiliated with the Perimeter Institute. Do you know Henry from Minute Physics?
No, I don't.
Oh, really?
No, I don't. Is that terrible? I'll go look it up.
No, it's not terrible. No.
Yeah, one of the people who works with Perimeter Institute
I see.
Has like a YouTube channel where he describes big physics conceps in like a minute. Physics.
Yeah. Mm-hmm.
Yeah, so we were just wondering if you might have known him, but
No, I should look into it. Yes.
I don't know if he still works there though. Does he?
He's got his profile up on the website. I don't know if he's still there, but I know he has worked there at some point. But.
Have you listened to some of his YouTube videos?
Oh, they're great. They're awesome. They're really like low level, so everybody can understand them. It's for like a really wide audience, and it's really good stuff.
Did you know about him before you came to Waterloo, or?
Yes. Yeah. I swear, I went on a tour of PI once, and I could have swore I met him at the end, but I didn't want to say anything in case it wasn't. I didn't want to be awkward. Yeah.
You'd think they'd advertise if it was him.
I don't know, maybe not. It's
it's not clear.
Yeah. Okay, so we have kind of an interesting opportunity right now, because you're the first professor that we've interviewed that has both a foot in the pure math world and in the physics world. So we wanted to ask, what was your academic path? What led you to be interested in both physics and pure math, and when did you sort of make the choice of what you would be focusing on?
Well, I mean, this may not be the most common answer that you'll get, but I really fell into math completely by accident. But it was not completely accident. I was educated in the French system, like in France, and then you need to, by the end of high school, start making choices. So your second last year, you kind of choose whether you're going to stay in humanities or science, so I chose science. And then after that, it was purely accident, because I really wanted to study architecture. And I think in the French system, if you're good at math, they encourage you to stick with math. So after that, you had to choose between biology and math and physics. And for the architecture, it was math and physics made more sense. And I was encouraged to do that because I was good at it. And My parents are also Romanians, so Romanians math is fine. Like it's not a strange thing to kind of think of. I'm not saying that it is. Obviously, we don't think that. Sometimes the people say, "What are you going to do with math?" It's like, okay, math is fine. It's fine. I come from a family of engineers, so they're all more applied. But it was like, okay, you want to do, okay, that makes perfect sense. So you do that. But then I still wanted to. I had no plan to study math. I wanted to study architecture, and then it's just in first year I got a scholarship to study math as an undergrad, and then science, and I preferred biology and chemistry, but first year the math courses. Biology and chemistry you need to maybe biology you need to learn a lot of things by rote, and I don't like that. So okay, I'll just study math because it's not it's simple. Well, it's not easy, but I just need a pen and paper.
Right.
And then I kind of did that, and then it just kind of snowballed after that. I wasn't even convinced after my undergrad that I wanted to do that, and then I just always had these opportunities, or even as an undergrad, of doing research terms, and then getting scholarships to pursue grad work. So every time I was like, okay, this is kind of fun. And then and then the only conscious decision that I made was I did a master's in analysis, and then which I found was quite interesting, and I was solving systems of differential equations, but there was some geometry in the background, and as an undergrad I had read some Milner, so I quite liked geometry, but I didn't really know that much of it. And then I decided that I wanted more to study something that had more global questions, whereas at least the analysis that I was doing was more kind of more local and more. So I was gravitating more towards having these more. I don't know if that's the right word, but a global question. Like, okay, what are all the things that you can say about not just around a point, not just local properties. And then I switched. And so, but that's the only time where I can really say is like, okay, I had this is a very conscious. If not, I don't know. I've always just like taken courses and enjoyed it and studied it. So there is no plan. There really was not. And then for the physics, I think it's just my PhD supervisor, who is a geometer, does what he does. Well, I mean, I'm still in the same area as him, but the objects are coming from physics. So this is. I guess I came full circle from high school where I was doing math physics. But I haven't done physics since then, so I keep on hoping, I keep on buying books that kind of explain a bit more the physics, but I don't get around to reading them, unfortunately. Maybe one day.
Hopefully. Yeah, when the math sort of dries out.
Exactly. Or what I do, I can just get more physics students. I've had physics students even for masters. I had a student who did a master's thesis on black holes, and that was fun, so so maybe that's the way I can do it. I can get these students who they have some interesting physics problem, and I won't understand it, but at least I'll have an idea of what's going on. So,
yeah. So, I'm curious, have you spent any time, now that you're a geometer, thinking about how the higher level forms of geometry could be applied to architecture, or has that sort of...
Yeah.
Okay.
I mean, and actually there is Ian Hamilton, who is one of the best geometers and topologists around, and he's at McMaster, and he is now the director of the Fields Institute, which is the math institute in Toronto. His son, Daniel Hamilton, has an office at the Fields Institute, and this was before Ian became the director, by the way. But anyway, and Daniel, his son, is very interesting. But so already, his father is a geometer, topologist, interested in studying shapes, and then when Daniel was doing his undergrad, he had an internship, and I think this was in England, in London, and he was working for an architecture firm, and this was a summer job, and then he kind of realized, oh, yeah, I would like to use some geometry, to learn some geometry for the problem, because and a lot of the structures more and more now when they build, when they're constructing a building, they have very intricate shapes, and it helps to have someone. I mean, obviously you need an engineer to kind of tell if structurally it's sound, but it helps to have someone who has a background in geometry and topology to even know if the shape is feasible. Like it could be even questions of curvature, you know, and or if you're kind of doing things that have, I mean, it's hard to describe here, but you know, like things where you're...
We don't want any Klein bottle buildings, for example.
No, but it could even just be that, let's say you're trying to do things that are made up of these little diamond shapes, but they're not just... Well, it could even be a grid, and if you want a certain pattern, is it possible, right? I mean, of tiling, right? Like, this is a geometric problem as well. You know, like, if you're trying to tile with a certain shape, you may not be able to. And on top of it, if it's not flat, but it's curved, that's even adding certain problems. And then you may even, in your building, there may be a hole at some point, you know, so this becomes topology. I mean, can you have such a shape? It becomes a question of triangulating your shape and understanding if you can put it, you know, kind of create such a shape using triangles with these types of properties. So he did a master's even in math that was already, he had that in mind. It was in topology, geometry and topology, but geared towards that. And then he now has a business where, I mean, he worked for a few years, I think 7 or 8 years for an engineering firm, and then now he has his own business, and that's exactly what he does. And not only is it applications to architecture, but also gaming, because you can imagine how the same thing applies.
Yeah, yeah.
And then, and also with designers. So it's one thing, and Yao, so you may know Yao, the mathematician, the Fields medalist, he even has, I mean, he's a geometer, and he even has a company in, I think, San Francisco, where that's what they do. They do a lot of computer graphics, and they have some mathematicians working there exactly because of that, right? When you're geometers, I mean, working for them. So, and we even had we've had some students who then went to work in industry who are geometers who were working for in computer graphics or other types of applications. So there are applications, and I think it's something that probably we should look more into and tell students about, because often you know, it's not everyone's going to get a job in academia, or not everyone may want to, like, right? It's not even just the question that you don't have opportunities, or you may not want to stay in academia your whole life, right? Like, there are all these reasons, and there are a lot of very interesting things that you could be doing, even with the geometry. Not just the applied math, right? I mean, in a sense, like, even this more theoretical type of mathematics has some very interesting applications. Yeah, so.
Absolutely, that's awesome. Now, just moving along then. What was the first kind of like mathematical result you remember producing? Like, even if it wasn't good enough to be published, like the first thing that you looked at that you'd done and been like, wow, I did this.
Well, I mean, because can I say that I read some questions before to prepare slightly for the interview, and when I was reading that one, I was trying to think, and I don't know, it made either sound a bit naive or slightly obnoxious, but I remember when I was even as an undergrad, I often just would just read things and try to just reproduce things myself, even if it was like my real analysis course. And then it's like, okay, there's a theorem, I'm going to just try to do it myself without looking at the proof, right? And just working for the definitions. So I think that early on I kind of just really enjoyed that, of trying to play around with it, and maybe had like this innate self-confidence that I could kind of do it. It didn't always work, but so I remember even just that, right? I mean, obviously highly non-publishable, but it was just the fact that is you're trying to I don't know, come up with a solution for something that, because you haven't seen, you know, it's not like I read the chapters. I was like reading along and kind of saying, okay, I'm going to try to produce the proof myself. And then I think for my first USRA was I was working for an analyst, and it was just finding a more geometric interpretation of a result, where you just had to, I mean, the idea was, just to rewrite the formulas that were being obtained, but in a way that you could interpret as, okay, this is telling us some information about some, I mean, obviously it's not exactly that, but the example would be, okay, that essentially this property is just telling us something about some surface in Rn that as opposed to just having a purely analytic kind of formula that you're just interpreting just in terms of the function giving you the formula, right? So,
right.
So I think that was the first thing that I did.
Yeah.
So.
Well, I must say, I don't think that's obnoxious at all. I mean, I think a
No,
lot
I'm
of us
just
do
saying,
that. Yeah.
okay,
Yeah.
then that's good. Maybe that's why we're all pure mathematicians. But don't you, but it's not like I was trying to prove anything. It was just more like, okay, I'm just going to try to do it. This is fun. So I think for me, it's always been just more about that, right? Yeah. And I guess you do it more and more, it's just...
I think it's an essential route to understanding the math you're using.
I agree.
Yeah. So on the other end of the spectrum of your mathematical accomplishments, what would you say you're most proud of?
Well, there are a couple of results that I have that I'm very pleased with, but it may be a bit complicated to describe. Well, I think that here, if I'm just going to give an idea of what is... So I'm a complex geometer. I work over the complex numbers and I work with things that are called manifolds, and these are just objects that around every point the space that you're working with looks like is diffeomorphic to an open ball in Cn. Okay, and on these manifolds you can have a lot of structures that you can put on this manifold, and I work a lot with complex surfaces, so these are things that locally look like an open ball in C2, and especially if you look at compact complex surfaces, these were all classified by theorem, and almost. The classification is a bit open, and a lot of these surfaces that come up in algebraic geometry have these usually when things can be described algebraically, they're a bit more rigid, they have more structure, so they've been studied a lot because there are more things that you can say usually about these using these more rigid structures. And I've been working on things that are non-algebraic, especially manifolds that are called non-Kähler, and what I've been finding interesting is to see what's often you use the fact that a manifold has these Kähler structures, especially if they're algebraic, to derive a lot of properties about the manifolds, but I think that in a lot of cases it's not so much about the Kähler structure, it's more there are other things about the surface that this is getting very vague, but that give you that the results some of the results hold for other reasons, let's just put it this way.
Okay.
So I've been kind of interested in seeing what's really guiding some of the results. That sometimes having the Kähler structure helps you in the computations or deriving. I mean, you have more. It's like being over the complex numbers. You know that your polynomial in one variable always has the roots, so you can use that. Like, okay, I know for sure degree n has n roots, and so it's useful to have that structure a bit more. So this is just the analogy, but for me, because I'm in these non-Kähler setting, I can't just use the Kähler metric and all its beautiful properties. I need to kind of work on but I think, technically it's a bit more challenging, but I think ultimately they're interesting because, okay, this is not very well put, but you really have to understand a little bit better what's guiding some of the results that exist, okay? And I have a couple of results in that vein that I'm quite pleased with, where we're able to, in some cases, for certain things, this is all very vague, but we should probably cut this out. But the point is that it's going to, that you're just able to understand really what's guiding the geometry, and it's not, it's not the Kähler structure that's really guiding it.
Okay.
And so I'm quite pleased with that.
Yeah.
There you go.
Yeah.
Well, there's certain types of metrics. I mean, a metric is something that helps you to compute distances between points,
yes.
and if you have a Kähler metric, what's very nice about it is that up to second order approximation, it has a very basic standard form that you can always think that, oh, it's kind of like the Euclidean metric, okay, I'm exaggerating a little bit, but it's really that, right? So you know that it will behave like the standard one you can give yourself that's the nicest, right? And then if you don't have that, well, it's just a more complicated object. But I don't think it stops some of the basic geometric properties of these compact, complex surfaces from existing. You just have to work a little harder, and yeah. So
Okay.
there you go.
Right. Okay.
Well, now the flip side to the proudest mathematical achievement is, what's the one problem you wish you could solve but haven't been able to yet?
I don't know. The next problem I'm working on. I don't know. I don't have a big problem. I know some people have these big... I think maybe it's just that. I think I'm kind of interested in this. I'll be very happy if I can understand... Yeah, I think I'll be just very happy if I'm able to shed a bit more light on some type of certain types of examples. Or I like working with examples, actually. You know, because some people, I have papers that kind of build the theory a bit more, but I like to then apply it and really see concretely what it means. And so, yeah, I don't know.
I think examples are probably paramount to the study of geometry and topology. I remember one of my favorite books was the Topologist's Picture Book. I mean, have you ever heard of it?
Yes, actually.
Yeah. It was pretty famous for a while, but it's a book of all these beautiful examples of topological spaces with interesting properties. It's just so amazing to see all the connections between the different abstract, vague theorems in topology made into real objects that you can think about and touch. So yeah, I think examples are absolutely essential.
I mean, on one hand, there's the whole thing also that when you're describing or when you're defining your geometric structures, you don't want them to depend on the picture, right? Because the picture can be misleading, and you're not thinking of counterexamples. But I think at the end, I do agree, you want some examples. And I think there's always you probably go from one to the other. Looking at examples helps you find new important structures and vice versa, right? So, yeah. Yeah.
Would you say you have a favorite example?
I mean, you mean an example of just math object, or just...
An example that you'd use in describing a property of math.
No, but there are a couple of examples of complex surfaces that come up a lot in my work that encapsulate a lot of, of the properties that have some of the properties that I'm interested in, and no.
Okay. What about
no, I can't say no.
What about a favorite theorem?
No, I don't have a favorite theorem.
Okay.
I was thinking of that. No, I can't say. I don't know. I'm not like that. I don't really think of that. I mean, you have some theorems that are very interesting, and but I don't know. I can't say that. Do you have a favorite theorem?
Do I have a favorite theorem? No, I wouldn't say so far. Yeah. Off the top of my head. Do you, Logan?
Off the top of my head, no. I mean, there's theorems that are really, really beautiful. I mean, I think
prime number theorem is always
prime number theorem is a great one.
Yeah.
It's elementary, but the mean value theorem is also I think it's a beautiful theorem. I mean, it's one of those things that's super intuitive, and then the argument for it just everything is. Nice. I don't even know how to describe it. I really like the mean value theorem.
What about favorite examples? I don't know if you have any favorite examples.
I don't know. Examples. It's kind of for me, examples are something that you use, or something that I would use if I didn't know how to explain it in a better way, right? Like if I couldn't give or if the actual definition of it wasn't super duper concrete, I guess that's when I would pull out an example to say, here's how it works. But
but examples are important. There's
I agree.
Nikki Cameron, who's at McGill University, one of the professors in the mathematics and statistics department there, who's a great geometer. And then I remember as a grad student, he would always say, for every new concept that you have, you should find an example and a counterexample. So there you go.
Yeah.
It's very important.
Yeah, I'd have to say, favorite example would be the Weierstrass function. Am I saying that right? Weierstrass?
We're Weierstrass.
Weierstrass. Yeah. Right. Yeah, as an example of a function that is everywhere continuous but nowhere differentiable, which was for a long time thought to be impossible. But then Weierstrass came along and showed it, and it wasn't. So
most functions are like that.
Yeah, actually, yeah. I think that's a dead subset of all functions.
Yeah.
But yeah. So, anyways.
Yeah. Okay. Well, do you have a favorite math joke?
No.
No.
I'm a very serious person. I don't tell jokes. No.
No. Okay.
That's fine.
No. Do you have a favorite math joke?
I have a favorite joke. This is not a joke about math. It's more of a joke about math teaching.
Oh,
So,
I see.
Yeah, so there was... no, it's not. No, you shouldn't be worried. Don't worry.
Okay.
There was a Russian professor who came to teach calculus at an American university. And he knew what calculus was, and he knew what topics that he had to teach, but he didn't know what order or how to exactly, teach it effectively to the students. So he went around to some of the other professors, and he asked them, what should I teach on the first day, or what should I teach in the class? And they said, okay, you should go through continuity of functions, differentiability, limits, then move your way up to integrals, and then double integrals, triple integrals, all that stuff. So he takes his notes, and then he goes into class, and he teaches, and then he goes back to the professors the second day and says, okay, what do I teach tomorrow?
Yes.
I've never had an encounter with a Russian professor yet, but I hope it's not nearly as scary as that anecdote.
Well, I don't know if it still exists, but there used to be this Math in Moscow program where you could go and spend a term in Moscow.
Wow. Yeah,
At an independent university there.
Yeah, there are a number of exchange programs you can do at Waterloo, right? Yeah, I was looking at some of them yesterday.
No, but this one is specific because if it still exists, it was funded by NSERC and also by the NSF, and it was students chosen from the American schools and from Canadian schools, and it was a smaller group, and then you'd go and spend the term there. So
sounds like a challenge.
Something to look into.
Yeah.
It's an interesting city, Moscow. I have a Russian collaborator, and I've been there several times. It's very interesting.
Yeah, it'd be nice to visit one day.
Mm-hmm.
So next, I'm interested. Do you have? Is there a most common misconception that people have about geometry or about math in general?
I mean, I think probably geometry makes more sense to people, but I think they think of math as being arithmetic. I think that's really the biggest misconception about math being just arithmetic.
Right.
Yeah.
I was curious. I said geometry at first because geometry is such it seems intuitive at first, right? It's all based on things that you can touch and feel. So you don't feel like there's any major misconception people have about geometry, higher level geometry?
No.
Okay.
No, and like I said, if anything, I think at least like this, they will think of a shape. They go, okay, it's a triangle, it's a circle, okay. So at least it's a bit more concrete as opposed to someone just saying, oh, you're a mathematician, you like numbers, right? I get that all the time, right?
Yeah.
I think that even as a geometer, it's easier to kind of explain a little bit, because that's the thing. I mean, a different Riemannian geometer, a differential geometer, who is interested in shapes and things like that, you can kind of explain a little bit how you about that you're just studying shapes, even though I don't think that geometry is a bit more broad than that in my mind. I really think it's even more general structures. It doesn't just have to be the physical shape of an object, but at least you can talk about that, right? And people can visualize it and make sense. But I think probably some other areas are a bit more complicated. I don't know.
Yeah.
Well,
category theory for one.
If you try to explain category theory, I mean, there's certainly, I think, at least some fields that are a lot more friendly to people who are non-mathematicians. Like, I mean, all the problems in like number theory are really easy to say. Yeah. Like, you could understand them with like elementary school math, but then their solutions are ridiculous, right? I feel like geometry is kind of in like the same vein as number theory in the sense that regular people have a better grasp of what it is. But I don't know.
Although I don't know maybe it's the same thing as one of my colleagues, Andy Unica, who's an analyst. I remember when they had several breakthroughs on the sphere packing problem a few years ago, and then I'm paraphrasing him, so I should be careful when I say this, but he was saying, oh, you know, maybe it's not the best, how do you call that, advertisement for kind of pure math, because in the end, the solution is pretty much what a grocer knows, you know, when they're stacking oranges, like the best way to stack it matches, right? Like the math after with these very sophisticated techniques, because it's extremely difficult problem. It's basically that, right? So
right. Given, I don't think a grocery store bagger would be able to pack 4-dimensional spheres or 24-dimensional spheres.
Perhaps. But at least in the 3-dimensional one, and so anyway. But whereas maybe I don't know, or sometimes the answer is a bit more surprising. And number 3, I guess it depends on the result.
Right. Do you have any results in mind that are completely misleading in terms when you try to apply a geometric perspective to it?
No, I think that if you pose it the question, I think the thing that's a bit different in geometry especially when you first work on it, is that often because you're really just trying to understand the structure of something, you don't often just have these clean questions that you're asking, right? So it's like, I'm trying to understand this better. Mm-hmm. And often the problem is maybe that you're not posing the problem properly, or and so you kind of refine that. So I don't think there's ever a situation, if you have posed the question well and you're using the right point of view, I think usually it's pretty consistent. Okay. I would say, yeah, I think so.
Okay. Do you have any mathematical heroes? Like anyone from history, and you're just like, wow. Great job.
No. I know, it's terrible. I feel so like a terrible person when I was reading these. No, I can't say that I have any. If I'm going to be very honest, I could have come up with a couple of names for you, but no. I think my heroes have always been more like, people from literature or musicians, composers. You know, it's. I guess when I was growing up, I was much more into the arts. So
really,
yeah.
Wow.
So that's why math was very much an accident for me.
Interesting.
Well, I mean, pure math's pretty artistic in its own right.
Of course, I don't disagree. So there is some mathematicians that I admire very much, but I can't say that I kind of grew up thinking, oh, I want to become so and so. That's never the case.
Okay.
Right.
Yeah.
Okay.
Okay. Well, what about
why? How about yours? I'm always turning the conversation on you.
Oh, that's fun.
You know, I like that. I like this dynamic. Yeah.
I mean, well, Euler obviously he's a big name, but I think I really like Riemann.
Riemann's a cool guy.
Yeah.
I'd have a beer with him.
Yeah.
Excellent.
I'd have to say, what's his name? He was the inter-universal type Mueller theory guy. The Shinichi Mizuki, was that his name?
I think so.
Something like that.
Something like
anyways,
that. Rhymes with it.
I just admire his tenacity and his solace. Like, this guy spent like 2 decades working on this theory that no one had ever heard of before to solve a problem that hadn't been solved for 100 so years, the ABC conjecture, and comes out in 2014 with like 20 papers about it, all by himself, and it's taken 3 years for people to like confirm that it's probably correct what he's all done. And there's only 10 to 20 experts of it in the world. Yeah. So I just, maybe it's kind of a stupid answer, but I certainly admire his. I'm an introvert, you know.
I think that mathematicians are in general introverts, and people mistake that because you can be a social introvert, right? I'm also very much an introvert, but I think I'm still approachable, and I'm pretty social, and I can have a lot of social interactions and enjoy them, but at some point it gets to a limit, and I'm like, okay,
exactly,
I need to be quiet for a while.
Unless you're someone like von Neumann, who was, I think, an exception to the rule. He said that a lot of his most profound thoughts came in moments of complete chaos socially. Like, he'd be in the middle of like a party, and he'd be writing on the couch or something, and he'd come up with something brilliant. But that doesn't happen to most of us.
Okay, well, I mean, if you don't have any like mathematical heroes, then do you have like a favorite like story from math history? Oh, okay.
Well, not that I can think of on the spot. No, I mean,
Okay.
I don't know.
Okay.
Fair enough.
Yeah. Right. A question we always ask everyone we interview, and I'm sure you probably gave some thought to if you read the questions beforehand, is...
I don't know if I made it to the end.
Oh, no? Uh-oh, okay, that's okay. All right, well, what...
Not that they were not riveting, but I've had a busy couple of weeks. I'm sorry, I should have been better prepared.
That's fine,
No
yeah.
worries, it's going well so far.
How would you describe your philosophy of math?
I did read that one.
Oh, okay, perfect. Great. So, do you think math is invented, discovered, somewhere in between?
I mean, I find it interesting. It's something that I do ask people that I meet, and particularly like some people that I really admire, some mathematicians who are living and that I really admire. And so, and for me, the way I think of it is more like, do you think, as a mathematician, do you think of yourself more as a scientist or more as kind of an artist or a poet or something like that? And I think it depends on the person, and for me, I would go more towards the artistic side of things, because I think, it's not just that you're looking for a solution, but then you're always trying to refine the idea and the argument and try to find the best way to think of the problem. And sometimes it really depends on the context, and you're trying to find every possible way and seeing how they all compare. So I think that if, not to say that scientists are, if I think of it just purely scientifically, but if you already have a solution and you have a pretty good way of implementing it, maybe that's good enough. But I don't know, for me, I think of more, I think myself more as an artist, yes.
Nice.
That's great. I like that a lot. Do you think, what's the reason you think people should study pure math? It doesn't have necessarily any application to the real world. Do you think there's a reason why people should be studying this stuff?
Well, I think that people should be studying more abstract things, but it's not just math. I mean, I could say the same thing for philosophy and just for history and for music theory, for music, or the arts in general. So I don't think it's just because of math. I think, of course, these things should be studied. Now, I also think that it's just such a personal question of just a personal choice, and it's just a question of taste. And I think that I've met enough, not just myself, but I've met enough mathematicians and also students, and seeing a little bit how they evolve through their studies, of sometimes you don't really have any choice, right? You just kind of realize that you're more gravitating towards something that's more theoretical because you enjoy thinking more that way, or you enjoy more how the questions are posed or what they're trying to say. And then others think at the beginning, because as a thing, when you first start out, because I guess one of the questions is also, how to become, or how to become a working mathematician, or all these things. I think that when you're first starting out, you have no idea when you're in high school what it means to be a mathematician. You have no clue. And not to do a music analogy, but you have a lot of that. It would be like when you're first young and you're learning an instrument, and you just think that the only way to become a musician is to be a soloist, right? If you're a classical musician. I mean, that's often because that's how you're trained, and then you kind of realize, no, I can play with others. Like, no, I don't have to be a soloist. Or same thing with a mathematician. Like, you have no clue what it means until you get to university, and you kind of try different types of math. And then also that you can collaborate, right? It doesn't mean that you're just by yourself with your problems. That's the thing. So, and I think that little by little, with all the courses that you're taking, and then all the interactions that you're having, you figure out what you like. And I think if you like pure math, it's just because you enjoy working on more on the concept of things and more on the formal aspect of things. But I think you'll, I don't know.
Okay.
Where did the question start? The philosophy? I can't remember. No, we're past the philosophy.
Yeah.
It was
about why
study pure math. Yeah, and I think, of course, one should just address very basic questions, and often math does, and pure math asks some very basic questions about the objects that you're looking at that are very natural and often extremely difficult to answer. And of course, these questions should be asked. Now, whether you should be the one studying them is then completely a question of taste.
Absolutely.
I think. So,
Okay.
and I'm sure you've already found that yourselves, right?
Yeah.
You probably, even in first year, had some classmates who, it's not that they can't do it, because it's also a question, it's not that you can't do it, but maybe you don't like it. You realize, no, I don't care about the theory. I'm much more interested in this course where I'm getting to apply it, or, you know, so personal.
Absolutely. I would agree with that. I think that's a good answer. Now, do you have any like research strategies? I mean, you were mentioning earlier, you know, you went to a conference just a couple of weeks ago, right? Now, is that commonplace in math, just to kind of like spark up a bunch of ideas, get everyone together and working on problems, or?
That's not as common. I think more conferences, most of the conferences are about you presenting recent results.
Okay.
And so you give these talks, and they should be about a recent result that you have. And then when there's time between talks, then you try, you know, there are people there that you maybe have conversations with, but often it's too short because there's not enough time. This was quite different because the point was not to present your own research, even though you all have expertise. Some people gave talks, but I gave a talk, but it was really about the basic results in the area. You know, some of them I have worked on myself, but you know, it was not supposed to be about my work. And the whole focus was about kind of starting these new collaborations and working on new problems. So, but unfortunately, I mean, it worked quite well. It was the first time that I went to a conference where it was just about that, and actually it worked quite well. And maybe there should be more of them. So maybe I've been thinking I should organize something like that myself.
Maybe.
But but I don't know what the strategy is. I think that the strategy is to work on things that you find interesting. Obviously, you also want to work on things that other people find interesting. Because, well, I mean, you know, you could be working on something and having an idea that not everyone is realizing is important right away. But I think it's good to... I mean, it's good to be part of a community, to get feedback, and it's more fun to kind of have people to share your ideas with, and but I also think that you should, I mean, this is just a personal opinion, but sometimes people, especially when people are starting out, they're thinking, oh, there's nothing wrong with being ambitious, but you know, okay, I'll work on this because this is a big problem, right? And what if you're not really you don't really like the area that much, or then so what, right? Like, there are a lot of big questions, there are a lot of interesting things that you can find that you also like, because it's hard enough, you know, research here, it's not easy, so it may as well be in something that you really enjoy. So even for me, right, I switched from analysis to geometry, and sure, I had to catch up a little bit after my master's, but it was well worth it, because I'm much more enjoy the questions that I'm working on now, so okay. There you go.
Right. I must say, you kind of making fun of rescind my answer of do you have any mathematical heroes when I said that guy that spent 20 years alone. I mean,
no, because I'm not saying, like, sometimes as a thing, I'm not saying that they're not solitary moments. But he was working on something that and then he did share it, right?
Yes,
it's not
he
like,
did share it. Yeah.
Right? So,
he kept it to himself. No, he didn't do that.
But I can also understand when you're working on a very big conjecture, some people will not tell others, even though because it's kind of dangerous. I mean, dangerous. It's not that it's dangerous, but it can be, unless until you're kind of sure what you have. And I'm not saying this at all because I feel responsible. It's going to go out there that other people will steal your ideas or whatever. It's just more the fact that you want to be sure that what you're putting forward is actually correct, right? You're not saying, "Oh, I have the solution to this really big conjecture," and then like it's completely. So that's why, you know. So like sometimes it's not so much that they're being solitary, but they're kind of maybe kind of keeping a bit quiet until they're pretty sure, or they're feeling quite confident, and then, you know, but that's quite natural.
Yes, yeah,
absolutely. Okay, well, I think we're just about out of time here, so we have one more question. Now, what advice could you kind of bestow upon us aspiring mathematicians who want to be working in academia one day?
Come on, this is the last leg of the race.
No, I know, but it's a tough one. I don't know. Well, really, that it's if you're going to, make it all the way through, to be lucky enough, because a lot of it is also luck, right? I mean, a lot of things have to come together to be able to work in academia, simply because you don't have as many jobs as in industry. But I would say that you have to think of it long term, right? That it's and then there's not just one path. You know, some people really, sometimes maybe people who last a bit longer is because they really enjoy it and they don't see, you know, it was you can't expect that it will work out right away, and then I'm not being negative when I say that. What I mean is that there's not just one path. You can't just think, oh, because I didn't go to this school and I didn't do this, I didn't do that, things won't work out, right? Like there are several paths to obtaining, to reaching your goal, and to not burn out, you know? So that's the thing, like it has to be fun, right? I know it sounds silly, but it should be fun. And a lot of the time, because it's difficult, you can have moments of being, you're very frustrated and you feel very stuck. And also to not be so hard on yourself, because I remember when I was a lot younger, I was a lot harder on myself, and well, you know, I'm not saying you shouldn't be ambitious, that, you know, it's different, but at the same time, you should be having fun doing it. So I don't know if that's good advice, but it's just that, right, that you there are many ways of reaching your goal, so it's yeah. And the good news is that there are a lot of people along the way who will help you, right? So to also, an advice is to sometimes I may feel awkward to kind of ask for help or get to know people or things like that, but don't be shy, right? Like a lot of people will be here to support you, and I've been surprised, always very pleasantly surprised at every moment in my kind of I don't know if I want to call it a career, but you know, in my evolution as a mathematician, there have always been some key people that I still get in touch with, right? That I still see at conferences, and it's always wonderful to see them. So, nice. You know, maybe as an advice to not be too shy, right? So even though you're an introvert, you know, even if you're an introvert, you kind of still interact and anyway.
Absolutely.
That would be my advice.
Okay, well, thank you very much.
You're very welcome.
I think it went very well. Thanks for coming on the show.
All